Hi physics students, this is the third video in this topic 4.2, which is traveling waves in your syllabus. And in this video I'm going to talk about something really important that will come up time and time again in this class, and that's electromagnetic radiation or electromagnetic waves. After that I'll talk about water waves a little bit, and then even though we've spent a lot of time talking about different kinds of waves as depicted graphically, I'm going to talk about some of the real nuances between displacement time and displacement position graphs, just to kind of sum it all up before we move into our next waves topic, okay? So the first thing I'm going to do is just simply define what is electromagnetic radiation. You hear this referred to as electromagnetic radiation, E&M radiation, E&M waves, electromagnetic waves. Really all these terms are talking about the same thing. And what this is it's a form of energy that's released in electromagnetic processes, okay? And I'm going to talk about what some of these electromagnetic processes are. Essentially what it is it's a synchronized oscillation of electric, that's a vector field, electric fields, and B fields. B stands for magnetic. So electric and magnetic fields, okay? And this is depicted right here in this little GIF animation on the right, okay? Here the red field, the red wave represents the electric field, and the blue one represents the magnetic field, which is actually coming into or coming out of the screen and going into the screen. You can see this is a 3D coordinate system here, okay? So some of these electromagnetic processes are as follows. Number one, accelerating charged particles. Number two, alternating current, which is really a type of electricity. And number three, transitions of electrons across atomic energy levels. And this last one, if you remember from your basic chemistry, the way the atom is structured, you have different spherical, you can think of them as spherical shells around the nucleus of an atom. And in those shells, you have electrons sort of hanging out, okay? And all three of these we're going to talk about in much more depth in this class later on, okay? And this diagram right here, it's sort of a still visual of these two vectors fields. Notice that the electric field and the magnetic field are perpendicular to the velocity and perpendicular to one another. So we say that E, B, and V are orthogonal, okay? And we're going to treat them all as a set of transverse waves. Well, E and B are going to be a set of transverse waves, okay? Electromagnetic radiation travels at about 3 × 10⁸ meters per second. This is such an important constant in physics that it has its own variable, and that's a small lowercase c, okay? And it can be characterized by wavelength and frequency, okay? I want to point out here that electromagnetic radiation is not the same as light. Okay, it turns out that light, or what we can see, humans can see with our eyes, what we can detect with our eyes, happens to be electromagnetic radiation of a very narrow band of what's called the electromagnetic spectrum, which I'll show you in the next slide, okay? So again, you want to make sure that you understand how really light is just one kind of electromagnetic wave. Most of the different kinds of frequencies of electromagnetic radiation we're actually not able to see with our eyes, and there are lots of reasons for that. I guess most scientists feel like it's an evolutionary thing, which I'll talk about in just a minute. We've talked about a little bit in class before, okay? And also light behaves, or electromagnetic radiation behaves as a particle called a photon. We'll study that later, but in this part of the course we'll talk about E&M radiation purely in the context of being a wave, okay? So again, light, what we see with our eyes, is a very small part of the E&M spectrum, okay? You should know that visible light has a wavelength of about 400 to 800 nanometers, 350, 750, somewhere in there. It's not a definite concrete edge, because these kind of, the blue sort of fades into ultraviolet, which we can't see, and the red sort of fades into infrared, which we also can't see. This little chart down here gives you some more detail into the approximate wavelengths of different colors. Now, if you look at the E&M spectrum here, this one is organized from low frequencies on the right to high frequencies on the left, okay? You can see low frequencies would be radio waves, microwaves, infrared. Okay, higher frequencies, ultraviolet, X-rays, and gamma rays. Now, we're bathed in all of these kinds of radiations all the time, from natural and unnatural sources, okay? But you should be aware that the low frequency waves have less energy than the high frequency waves. And that makes sense when you think about it. A higher frequency wave, there'll be more waves hitting you per unit time, so therefore you're being exposed to more energy per unit time than a low frequency wave where there might be not very many waves hitting you per unit time, okay? Now it turns out that our sun, our star in our solar system, emits mostly in this part of the spectrum, which accounts for the sort of a yellowish, I guess reddish, yellowish-orangish color to the sun. But more importantly, this has great implications for life on Earth because it turns out that if you were to graph the intensity versus frequency of sunlight contains all the colors and all the frequencies of visible light. It turns out that there's a real marked peak in the visible part of the spectrum, okay? And it's thought that that's the reason why we have sort of evolved to see that part of the peak intensity of the sun, which I'll talk about all this later, but it's kind of one of those interesting things in science that leads to a lot of different theories, okay? Now here's the wave equation for electromagnetic radiation. We use C for the speed all the time. It's 3 × 10⁸ meters per second, okay? And just a little comparison of the wavelengths of visible light, okay? So red has a much longer wavelength than blue, for example, okay? And red also has a much lower frequency than blue, okay? So red has less energy than blue light, okay? And again, increasing frequency, increasing energy. I have this little word here, danger. It's because ultraviolet X-rays and gamma rays can actually cause cancer in living cells because it ionizes atoms inside those cells because it has enough energy to do so. Okay. Few sources of electromagnetic spectrum regions. All types of these waves are produced in nature. Okay. Turns out that well, I mean, you can look through this yourself. So radiation from nuclear decay, very high energy, very dangerous, all the way down to thermal radiation, as we talked about before, as a form of infrared radiation. Background of the universe, microwave, also your oven, etc. Okay. Now, what's cool about this is that we can look at different things through different parts of the spectrum. So, for example, if we look at the Crab Nebula, which is a nebula in the night sky, of course, through the visible part of the spectrum, or what we see, it looks like this. If you look at it through different filters that only show, that only detect electromagnetic radiation of certain frequencies, it can look quite different. So this is what it looks like in terms of radio waves, infrared, and X-rays. So it looks very, very, very different depending on the way that you're looking at it. Now, a word of caution, obviously, we've converted radio, infrared, and X-rays into visible light in order for our eyes to actually see these images. This is thought to be this. You can think of it as this is what it would look like if your eyes were able to see radio waves. The Crab Nebula would look like this, for example. So pretty cool. Okay. All right. So again, C equals F lambda. The wave equation for E and M waves. All types of E and M waves are also produced in nature. Let's go ahead and do an example. I think we've actually done this example before, okay? So the speed of radio waves in a vacuum equal to the speed of light is 3 × 10⁸ meters per second. Find the wavelength for an AM station and an FM station, okay? For the AM station, and whoops, the FM station, okay? Actually, it looks like I didn't solve this problem right here. It looks like I set it up, okay? 91.7 megahertz, let's just do this one. It looks like the wavelength is about 3.02 meters, and you can figure out what the wavelength is for A. It's a very simple application of C over F. I have actually here V, but you could use V or C for the speed of light if you want to, okay? It's all the same with the wave equation. Okay, so again, to many decimal places, that's what C is in a vacuum. As you know, when light or electromagnetic radiation goes through more opaque substances or substances that are transparent but have more molecules in them, the speed of light is actually slower. It actually slows down, and that's why we saw refraction through that glass with the laser beams and so forth. Okay, you should be generally familiar with approximate light signal travel times. Just have an idea, be able, don't memorize these, but be able to sort of intelligently guesstimate, as it were, some of these times, okay? So it turns out that the time for light to go 1 meter is 3.3 nanoseconds. That's pretty small, okay? A light year, you should be aware that this unit called a light year is not a unit of time, it's a unit of distance, and it's the distance that light travels in 1 year, okay? And these are some terms like a parsec, These are some terms that we'll talk about later when we study astrophysics. It takes light 100,000 years to cross the Milky Way galaxy. I mean, pretty amazing the scale of things in the universe in terms of distances and time, okay? All right, I want to switch gears here and talk about water waves. I've talked about water waves a little bit. I've alluded to the fact that they're more complicated than transverse or longitudinal waves, and they're neither, okay? So water particles near the surface move in sort of a circular path, and they give the water particles both transverse and longitudinal components, but as a simplifying assumption, we treat them as transverse waves, okay? So here's a picture of water waves breaking into the shore. This is an amazing video of I think this is off in Mavericks off of California. Anyway, it's a video of this guy surfing this unbelievably big wave, okay? And of course, this shows the power or the energy that a water wave contains, right? I mean, it's just an amazing amount of energy can be carried through waves, okay? All right, another look at water waves. This is a great little GIF that basically shows you the rotational motion of a couple of points on the surface of water, okay? You can see a couple of things here. The horizontal displacement of the medium, okay, decreases with increasing depth, okay? This is really cool. You should spend a little bit of time looking at this GIF right here, okay? Now, this is a simulation of a ripple tank showing peaks and troughs, okay? Very cool, okay? So again, we treat water waves as transverse waves to make the physics easier. So, you know, this ping pong ball resting on the surface of the water, we treat it as going vertically up and down, but we know from experience that things floating on the surface of water with waves going through them actually move slightly horizontally. Well, this is the reason why. You should be aware of that, okay? Okay, I want to talk about graphs in a little more detail. Displacement time graph, okay? Obviously, we know that the x units, the horizontal units, are units of time. Therefore, peak to peak or trough to trough gives us the period, okay? So from this period, see if you can figure out from this graph, see if you can figure out what the period, the frequency, the amplitude, the wavelength, and the velocity are. See if you have enough information here to do this by pausing the video and trying it on your own. Okay, these are the numbers I got. The period just measured from peak to peak or trough to trough. The frequency is 1 over that. The amplitude, pretty straightforward. I've got this in terms of meters. Turns out that without more information, you can't tell what the velocity and the wavelength are, okay? Because remember, you have the wave equation, which is v equals f lambda, but you only know f. You have 3 variables, and you only know one of them. So you need a little more information, okay? So this underscores a certain point. Number 1, you can't get the wavelength from a displacement time graph directly. You have to have some other information or have another graph. Number 2, what appears to be the wavelength, which is the distance between crest to crest or trough to trough, what appears to be the wavelength is actually the period. And number 3, as with motion graphs, the slope is v of t. Okay, so that's really important, all right? The slope of y of t in this case is v of t, okay? In other words, y prime is v of t, d by dt of y of t, okay? So displacement position graphs, okay? On the x horizontal axis, there are units of distance. And these graphs look like essentially what you would see if you had a camera to the side and took a picture at a snapshot in time, okay? Therefore, peak to peak or trough to trough, this does give the wavelength, okay? Now see if you can figure out what these variables are from this particular graph. Okay. Now, turns out that you can't tell what the period is, not directly from this graph. You need more information, and therefore you can't tell what the frequency is. You can obviously tell what the amplitude is. You can figure out the wavelength, but again, you can't figure out v even though you have the wave equation because you have v equals f lambda and you only know one of the 3 unknowns. Okay, so the important facts about displacement position graphs are as follows. Number 1, you can't get the period from this graph directly. You need to be told more information or have another graph, such as a displacement distance. Number 2, what appears to be the period is actually the wavelength. Okay, and number 3, the slope of y of x, in this case, it doesn't really have a physical significance. It is not the velocity. Okay, that only makes sense when you're differentiating with respect to t, the displacement graph. All right. Okay, now if you put them both together, and this is often, you'll often see questions posed to you like this, you put them both together, you have a displacement time graph and a displacement distance graph of the same wave, then you can get all kinds of awesome information from it, right? Okay, so these two graphs that I just showed you actually depict the same wave or the same oscillations. Now, putting them together, it's very easy to figure out what these 5 variables are, okay? Here's my period, here's my frequency, the amplitude. I can obviously read the wavelength, and of course I know what the velocity is according to the wave equation, all right? So make sure that you can double check these numbers and ascertain what these values are for given 2 graphs like this depicting the same oscillation or wave motion, okay? Now, a huge danger, I've alluded to this in class, the displacement time graphs and the displacement position graphs look exactly the same at a glance because they're both sinusoidal graphs. They have I've seen so many students make mistakes thinking one is the other, but of course they're very different, as you know now, okay? I just also want to point out that the equilibrium position is not always at y equals 0. Well, why not? Okay, I want you to think about that. Well, if, for example, you have to think about what the physical phenomenon is that's being modeled by the graph, okay? For example, in this case, if you put a mass here, the equilibrium position with the mass on it is not the same as the equilibrium position of the string. And if you add or subtract mass, you would actually change that equilibrium position. So you have to be really careful of that, especially when you're doing laboratories and things like that. Now, in the case of a pendulum, you should ask yourself the question, you know, is the equilibrium position always in the middle? Okay, well, I guess it is, but you can probably think of situations where it might not be, and we can maybe talk about that in class, okay? Okay, let's do a couple of examples, and then we're going to wrap this video up. So pause the video and read this one. This kind of problem for you should be pretty straightforward at this point, okay? The graph below shows the variation. This is a displacement time and a displacement distance graph of the same traveling wave, okay? And I'm asking you to determine wavelength, frequency, speed, and displacement. Okay, wavelength, straightforward. Frequency, right, is 1 over the period. The speed, you just use the wave equation. A more interesting question, what is the displacement at 0.35 milliseconds? And all you do is you just read the second graph, okay? At 0.35, it's somewhere down here, right, which is negative 1.6, okay?